Okay, thank you everybody for staying around. And this is the last talk of the summer school, and it's more like, I hope, a discussion of the stuff that I've been working on or stuff that I'm thinking in light of everything that's been happening. So so feel free to interrupt or ask questions. And I changed it a little bit from what I had on the website. Okay, so so what I've been thinking about and trying to move towards is more related to try to exploit the advances in AI for science and also for science of science. As you probably have seen, we have so much opportunities with data sets, but I believe that it's just so much more stuff that we could extract from data that we cannot access at this moment. So there are data sets about open access publications. There are data sets about data sets, chemical components, so many things, biological entities that are hidden in publications and in other data sets. So I think AI can help with those things. But today I want to talk about, I think, opportunities that we have for using these techniques for science and science of science in general, and also some challenges that I found with the work with my students. So a lot of this stuff, some of the work that I will present hasn't been really published yet. It's just some preliminary results, parts of perhaps grants that were rejected recently. So I wanted to just put it out there for you to see. Okay, so none of this stuff would have happened without the help of my students, Han and Lijen, who you probably know already, and the collaborators. I ran the lab here. Well, I was running in Syracuse, and I'm moving to Boulder. And through the lab, I've had more than 20 students helping me, master students mostly, and the general support of funding agencies too, and an array of amazing collaborators. So a lot of the stuff that I do is a combination of multiple fields. So I do science of science, but I also very interested in AI and machine learning, and I also develop tools. So I think it's very important that if you develop new ways of understanding the literature or extracting information from papers or images, that you make that available as a tool, as a software that someone can use. And I'm also interested in potential biases that we have if we use data that is historical, issues of fairness, transparency in the kinds of policies that we recommend, science of science policies. Okay, so the stuff that I've been doing is related to 3 steps that I think are very crucial in science. And it's just a very cartoonish view of how science works. So these 3 steps that I will describe are just, of course, very small pieces of the entire scientific process. But you can think of science and knowledge production as starting from discovering the boundaries of what we currently know. So you go to a library, or you go to Semantic Scholar, as we saw in the last presentation, or Google Scholar, and you say, okay, this is what people publish this year. This is the latest and greatest, and that's where I will start my research. And then you say, okay, I'm going to choose out of the potential boundary of science. This is what I will work on because I believe this has the most impact and the most novelty. So nobody else will be working on this, presumably. And then you submit something, you produce your results, and your peers will evaluate how the quality of the results. So essentially, you will have a peer review of the correctness of your research. Now, the problem is that a lot of these steps, evaluating the boundaries of science, selecting what is novel and impactful potentially, and then evaluating the result of others, it's all done by humans, it's all done by scientists mostly. So it's very time consuming. It's a very important work, but it's time consuming. And if you look at at a survey that is already old, it's, 8 years old, but it was a survey that asked scientists, okay, how they spend their time over a week. You see that for a lot of the activities that are involved with scientific discovery, with selecting topics and reviewing, is very small compared to all the other activities that we do as scientists. So it was very, very tiny. We spend most of our time in meetings, class preparation, administrative stuff, writing emails, but very little to science itself. So that there are potential biases, but also there are potential delays, but also potential biases because, well, we're using our own experience to evaluate others' work. So we could be introducing all kinds of issues. And also, when we evaluate the correctness of others' results, as we'll see there, it's very hard for some of the things that are harder to understand, like statistical problems or graphical integrity issues. It's hard for the human eye to detect those things. So there is a research search in problems of research integrity. Now, we have so much data available these days, and stop. I mean, if you have questions, please stop or type in the chat. I'll read them. You don't need to necessarily, ask them out loud, but comment. I would love to hear your comments on this. But we have just so many data sets available. I started working on Science of Science a long time ago in scientific time span, and back in the day, I had to create my own web scraper to access Scopus, and Scopus, when I was at Northwestern, Scopus blocked access to the entire library of Northwestern, and the Northwestern library complained really strongly against our lab, saying, please stop, accessing the data. But now you have access to so many data sets that back in the day, you didn't have, access to. So only a few years ago, Web of Science was offering their data sets, and I believe they were charging around $300,000 to access the entire publication and citation data sets. I don't think they're doing that anymore, or maybe they changed the price a lot because of all these great alternatives that we have, or we had. Microsoft Academic Graph, OpenAlex, PubMed Central, which has data sets of open access publications. So you have full text, images, everything. You have access to grants, the grant information from, at least in the US, from around 12 agencies. Yes, please go ahead, Asghar.
Yeah, I couldn't see the Scopus. You are not preferring to work with Scopus or just access problem?
Yeah, I guess I was mentioning that I had problems with Scopus when I started. I'm talking about like 10 years ago. And I had to scrape their websites. I don't think they had an API back in the day. So I used a Python script to scrape their website. They blocked me. But now they do have an API, and it's pretty good. And Sylvia says that they have access at the ICSR lab. Good for you. But yeah, like I don't list it here, but it's an alternative as well. And you have data sets about grants, as I was saying, and about data sets themselves. So you have Figshare. We analyze that in a couple of our publications, and we can know who published the data sets, where they're available, which publication is related to that, etc. Okay, so I guess the stuff that I'm trying to work, and this is like a big view of what I'm trying to do, is to think about, okay, a lot of the stuff that has been happening in Science of Science is, okay, we have a data set of how science was done in the past, so we could understand, correlations among things for the different steps of science, of knowledge discovery, innovation assessment, and correctness. So we could see, okay, this is how things are, in the data that we see. And then I'm also trying to see, okay, what are the mechanisms? What are kind of the causal relationship between these things? I'm trying to use causal inference to establish, okay, if you do this, then that affects causally the outcome of any of these steps. But then another thing that I've been thinking about is, okay, these are the mechanisms, this is how science has worked, but how can we optimize science? What are the things that perhaps we're not doing well, or we could be doing much better, and we are just biased because of the ways in which we have been doing science for 100 years. So what are the new opportunities that we have? So I'm very inspired by the work that Tom was talking about, because you know, it just opens so much opportunities for us to think about how to optimize and intervene in science. So I will talk about 3 projects, but I will talk about perhaps about 2 that are the most important for this presentation, at least. One is related to biases that we have in peer review, and that's related to how we assess the correctness of others. And I will talk about what I call computational integrity, which is a system where we have developed for detecting problems in integrity in scientific publications. And then, as I've been working with data sets over many years, and I see the work that has been done in AI for detecting biases, I will talk briefly about biases that might be present in the data for science of science that we should be aware of. Okay, so I guess in trying to understand factors and associations and correlations that are related to scientific careers, I have this very old paper now, 10 years, that look at potential factors related to future H-index. And I know that there are many drawbacks or very many you know, bad things related to the H-index. So take this with a grain of salt. But basically, we look at a very simple analysis of neuroscientists, and we look at many features and try to assess with a very simple equation, just regression. Okay, what are the factors? For example, the publications, the journals that you publish in, your colleagues, your mentor, etc. We have like 18 features. What are the things that are most important for predicting your H-index in a number of future years? So we look at 2 years all the way up to 10 years. And we discovered that these are the most important factors. So this graph is showing, okay, as you move forward, how well what are the factors that are more important? So if you look at, you know, up to 5 years into the future, we found that using the H-index today, it's very important. It's the most important thing. So here, importance is you know, how big it is, regardless of the magnitude, regardless of the sign. So H-index is very important for 5 years, but as you can see, other factors become important as well. Your productivity becomes important, and also how many papers you publish in different journals, like how broad is your publication output. And if you look at 10 years, for example, all of those factors become like very different to tell apart. So it's really important not just to look at the H-index today, but you should look at, you know, what is the broad set of venues in which you are predicting. Are you predicting top venues for your field? This was, again, neuroscience, so it's restricted to that, although we did a couple of controls. But this is all association, so it's not really talking about mechanisms. We try to speculate about potential mechanisms, but that will be ideal to look in the future about what are the causal relationships between what you do today to your potential future H-index. And our prediction was relatively better compared to just using the H-index, and people have reproduced this in different fields, and they have improved this prediction performance much more than what we did 10 years ago. Another thing that we started investigating was, okay, what are how you should, as a mentee of postdocs and your PhD advisor, how you should combine their topics so that your success is maximized. And this is a paper that we published with Stephen. I think he talked about this last week. But basically, the take-home message is that You should try to not be related to your PhD advisor, and you should be perhaps more related to your postdoc mentee advisor. So once you move into a postdoctoral position, you should kind of move away from your PhD and learn the new techniques of your postdoc, because that's going to be related to the odds of you participating in academia. So this just doesn't look only at citations, which is the H-index, what the H-index uses, but this uses it on the content. So we're getting at data that's much more fine-grained. Okay, but how do we choose this topic? So I talk about, okay, the mentors. You should choose maybe a postdoc that will teach you something different, so you get away from from what your PhD taught you. But how do we choose that? Well, in the past, well, I guess recently most of us use Google Scholar, of course, but there are so many new alternatives, and I encourage you to try them. Semantic Scholar, one of them, Connected Papers. I don't know how many of you have heard of it, but it's a really nice search engine that allows you to find relationship between papers and forms a graph. And there are many, many other alternatives. Now, the problems is that many of these systems are closed source and proprietary, even though they are Semantic Scholar is open, but there is no like repository to understand how they are ranking things. It's non-profit, but they are still trying to, guard yeah, there is another research rabbit that AI that is being shared on the chat, but none of these things make their code available. So with a grant from a couple of years ago, we propose to create a system that I checked today and is down, unfortunately. And this is just one of the problems with trying to run one of the systems as an academic. It's just, it's like an engineering problem as well. Today is down, but it should be open, should be available in the next couple of days. But basically, we created a recommendation system that would allow you to find the boundaries of publications and the boundaries of grants simultaneously. So you will find something, and then it will recommend, okay, given the things that you like, these are the things that are related in publication space and grant space. Okay, so now I'm going to move on to potential problems that we have in peer review. Okay, so the first chunk was, okay, we discover the data that is available, and we discover potential publications. But okay, once we submit things, let's see how our reviews are evaluated by our peers. Our papers are evaluated by our peers. So one thing that we investigated, and this paper should be coming out soon. It's been so crazy. I think this paper has been under review 3-4 years now. So partially my fault and the pandemic. But anyways, we have a data set of +1 papers reviews and of the neuroscience section, and we have 8,000 manuscripts, thousands of authors, thousands of reviewers, and thousands of reviews. Okay, so one of the things that we wanted to understand is the effects of potential biases when the author suggests a reviewer. So many journals don't do this today, but many others do. And I think we don't know the numbers, but even when you submit a grant, sometimes you can say, I suggest this person to review my grant, and I suggest this person to not review my grant. +1 used to do this. When you submitted a paper many years ago, they will say, okay, suggest reviewers and oppose reviewers. So we want to understand the effect of that process, okay? And in one graph, you will understand the effect, okay? So what we did, we just map the decision. So you submit your manuscript, and we're going to look at the rounds. The first round of review, the first reply that the reviewer will give you. We're going to map the outcome of the reviewer. So they suggest rejection, major revision, minor revision, or acceptance immediately. And we're going to map that linearly. So it's going to be like a point here in this y-axis. Okay. And we're going to separate that by the type of reviewer. Was it suggested by the author, suggested by the editor, or was opposed by the authors? Sometimes the editor invited to review people that you oppose. So that was kind of fun. And we see immediately that there is a significant difference across the review rounds in between these groups. So if you oppose a reviewer and he gets invited to review your paper, it will be a significantly lower a lower judgment of your paper, in the sense, it will be more likely to be a rejection than compared to what was invited by the editor, who was invited by the editor, compared who was suggested by the author. And that's that's continuous throughout the rounds. And if you compare all the rounds, you see the significant difference among them. Okay, so there is this cumulative effect. The other thing that we looked at is how likely are these different groups of reviewers to accept a paper, how they affect the timing, basically. So are they really good? So if you're suggesting a reviewer, are they really going to say yes faster than if the editor is inviting someone? And we see actually the opposite. We see that the author-suggested reviewers actually reject invitations more often. So they, in a sense, they delay the review process because they reject the editor wastes time inviting them. In terms of quality, and this is the quality assessed by the editor, the quality of the reviews are actually lower for author-suggested reviewers compared to editor-suggested. There are many caveats, of course, because the editor is inviting the editor-suggested reviewers. Of course, maybe the editor thinks very highly of these reviewers, so there is a bias there. Now you can think, okay, the editor will be judgmental enough, or will have criteria high enough to say, okay, there is a bias here, so these are author-suggested reviewers, so I'm going to incorporate that in my final decision, so I will correct for any of these issues. Okay, so if we look now at the final outcome of a paper, like, does it get rejected depending on the panel that review the papers across all the steps? Or not? Are there differences? And we see still huge differences. So if we split the panels, and this is across revisions and just looking at the final outcome of a paper, we see that if you get a panel of all editors suggested, so no invited, not opposed, not suggested by the author and not opposed by the author, we see around 65% acceptance rate. But if you have a panel of all suggested reviewers, the acceptance rate shoots up to close to 90%. So there's a huge, almost 20% points of difference between these two panels. So Nihar talked a little bit about ways of improving upon this, and computer science has been a pioneer on doing this. And the basic idea, he talked about it already yesterday, but the basic idea is, okay, maybe we don't want to ask authors to suggest reviewers. Many journals don't do this anymore. What about if we kind of automate this? Okay, what about if we take the papers and reviewers, we compute some sort of vector that represents them, and then we do some sort of alignment or affinity among the papers and reviewers. Then maybe we can do some sort of mathematical optimization of this. And this is what Nihar talked about yesterday. Although he was more explicit, in this case, I'm trying to, well, A, here's the distance. So I guess you want to, not the distance, the similarity A with the affinity. So you want to, not similarity, the distance. So A will be the distance, so you want to minimize that. So you want the papers and reviewers to be as close as possible. But as he mentioned in his presentation, there are some problems. But anyways, we proposed this. We did something like this so that we avoid using author-suggested reviewers or author-opposed reviewers. And we've been using this system for many neuroscience conferences with a lot of success. And we have codes, though I'm not sharing it here, but we have a GitHub repository. We have the code to set up this website where you upload the papers and reviewers for a conference setting, and it gets matched to your, papers get matched to reviewers with some constraints. In fact, your assignment to mentors for this summer school uses a system that is similar to this. So there was no human intervention from me. I just set up this program to find, based on your ranking of who you like to meet, you know, who will be assigned to you. Okay, so I guess I'm a little yeah, I think I'm okay, but a little back behind on time. But basically, we have a lot of opportunities for using AI. I think for extracting information from publications. We have so many data sets available that we should really be taking advantage of these things. So we'll look at, and I talked to Nihar already, we should be looking at other kinds of things that we should optimize, ideally, you know, optimizing how we assign reviewers to papers. Okay, so I'm going to move on now to another project that is really, I find really interesting and important, and I call it computational research integrity. So research integrity is this field that tries to evaluate, you know, that the research has, you know, obviously integrity, that is correct, it's reproducible, it has all these features, so that, you know, it's robust and it's like using taxpayers' money in the best possible way. Unfortunately, there are many cases in the literature of scientists who fake their data. Now, here I will focus on a particular kind of faking, and that's image manipulation. Okay, so there was this article in the New York Times some years ago about a scientist from Ohio State University who published very prominent research on cancer, and very shocking, I mean, very amazing results. So other teams, of course, were trying to reproduce this result, and they started noticing duplications in the images. So this is a kind of experiment called Western blot, or at least this image is a Western blot. So it's the result of an experiment. Basically, this zero chance that you have duplications in these little gels in this image. Okay, it's a very, very small chance. So, so they complain about this, and they ask the researcher what was going on, and the researcher, you know, started to not replying to the emails, and then the New York Times article came out. Basically, the entire line of research was called into question. I don't believe there is a result of this research, in the sense of I don't believe the Office of Research Integrity in the US has sanctioned the researcher. It just, you know, there's been a lot of retractions. We have a more recent case in Duke University where a postdoc found similar problems. These were much bigger problems, but one of the issues was image manipulation. And just to make the story short, there was a final settlement between Duke University and the Department of Justice of $112 million. Now, the interesting part is that the postdoc who was a whistleblower got a third of the award, because it turns out if you help the government recover money that was fraudulent, you get a third of the award. So think about that. So so how are these cases discovered today? Well, they're discovered through human processes. So we need, you know, peer reviews, looking at potential manipulations. You need whistleblowers, the community, or the research integrity. The problem is that this is slow, of course, it could be inaccurate and dangerous for whistleblowers. So some of these whistleblowers, you know, had to endure years of harassment by these prominent scientists. There are many websites that report on these issues, but can we do better? So another line of my research is to try to develop computational methods to discover problems in image manipulation. And I believe so far in this, so if we take a page from the AI book, these methods, automating image detection and image manipulation detection, has been bad, or it doesn't work too well, because the data sets that we can use to apply AI to learn from are not that big. So the data sets have been in this regime here, really small. So we've been working with my lab to produce bigger data sets to improve how much we can use AI so that we can achieve performances that are much better than anything that we've tried before. So I will show a little bit of this research on detecting manipulation. So we developed a technique to detect, we adapted really techniques from media forensics to detect manipulations. We use a dump from 2015 of open access publications, so we have access to the paper and the images. And this is basically the procedure. We apply the automated technique, and then we have a panel of reviewers that went through these manipulations and judged them to whether they were fraudulent or not. Sometimes you have reuses that are okay, so you have zooms in an image, but sometimes you have reuses that are not okay, like rotations and things like that. So I won't go through much of the details of this, but basically we have a pipeline that is, again, very standard for media forensics to extract these features from the images, and we do matching. So we have the image, then we extract key points of the image, and then we do matching. So we need to find areas that are similar. So to do that, we need to do something called nearest neighbor search. That's very computationally intensive. I won't bore you with the details, but basically we do an approximation. If you want to learn more about this, it turns out that I'm giving a talk in a summit in a week or 2 weeks about this. So if you want to learn more about that, go to Race Summit. It should be online in about 2 weeks. I explained this because it's a very large scale search process. So these are the details of how it works. Basically, and then by the end of that process, we find the nearest neighbor. So and you can already see some suspicious things, like this is closer to this, so there is like a duplication of this panel. But there are some false positives, so we do some cleanup, removing image text and things like that, and we find duplications. So we apply this technique to all the images, and we ask human labelers to go through them. And to make the story short, well, these are some examples of things that we found. So we are able to find things within the images, across articles, across journals, so it doesn't matter, the system doesn't care. And you find all kinds of manipulations, rotations, just basic copy paste, changes in magnification, etc. And we found the human annotators had a relatively decent agreement on the things that they found. And if you want, like, the take-home message is that the manipulation is relatively small. So if you have 3 reviewers, about 0.5% of all the papers have problems. So it's not a huge number. But if you start focusing on papers that are about biological images, and if you care about being very careful, and then if one of the reviewers out of 3 says that there is a problem, then you get a number that is like 9%. Okay, so if you are really careful, there are like 9% of papers out there with biological images who might have an issue. Okay, and these are some examples of the stuff that we discover, and I will just skip that. We'll develop other things related to potentially discovering graphs that are not, I guess, they violate some graphical principles. So one of them is proportional ink violation analysis. So I don't know if you've seen this graph, but this graph, I think, was supposed to be showing how much harder Germans and UK and British and Romanian people work compared to the rest of Europe. The problem, however, is that this graph doesn't start from 0, so the differences look much bigger than they actually are. So the difference between Germany and Poland is to like an hour more per half an hour more per week of work. So it's not really huge difference, but if you kind of look and zoom in a certain area of the graph, you have this kind of misleading difference among conditions. Okay, so this happens in science too, and this was pointed out in the book by Carl Beckstrom and Jamie West and Colin Bullshit. And with Han, who is here, we had a paper in PLOS Computational PLOS Biology that developed a method to discover these issues, and it goes through the details of this. It has many different steps, and we have relatively good performance for each of those steps. And we found that around 5% of publications contain these kinds of issues. So there are graphs that are misleading, or not intentionally misleading, but they have principles of graphical integrity that are not being met. And we have differences across fields and across countries as well. Okay, so this idea of using computers to try to analyze graphical integrity issues is now part of a conference, and we got funding for a conference that will happen next year in Washington, DC. We hope to make it hybrid so that everybody can attend. So it's called CryConf. And we are also running some competitions to encourage the community to improve techniques for detecting issues in scientific papers. So we have two competitions. One is text paraphrasing detection and data to graph matching. So it turns out that when they're doing investigations, they have a bunch of, let's say, Excel files, and they have a bunch of graphs, and they want to know which Excel file produce a certain graph. So that's data to graph matching. And paraphrase is, it's self-explanatory. It's not just basic plagiarism of text. Now they are like paraphrasing, so they're being more sophisticated, but still is a form of plagiarism. So we developed tools that's similar to Eileen, but is a tool that I developed at Syracuse, and is being tried for detecting potential graphical integrity problems. And it's being tried by, I cannot mention the names, but it's by the US government, by publishers, and by editorial managers, so that running it on every submission. Okay, so I will quickly move through the third part, which is, to me, one of the things that is very excited about too, and this is related to Lishan's work. And this part, we try to discover potential biases in the data that we use in science of science. And I guess I'll show just this graph. Like we use a lot of data on scientists, publishers, institutions, funders, and related data sets from that. But we have potential biases that are influencing many of these things. Gender biases, race biases, as we saw from Aaron's and Dan's presentation on Monday. We have also prestige biases, socioeconomical issues that are influencing all the aspects of science. So we have to be careful. And we also have people that are maliciously producing data that is fabricated, right? So paper mills, predatory journals. So we have to be careful for those things. So I will quickly jump through these. With Lishan, we developed this technique to try to understand if there are biases in the language that we use in science. And it turns out that we do have biases. So if we have kind of, if we have text that is related to science in some way, academic terms, and this is a technique that I won't go into details, but basically if it is a dot that is below 50%, there is some bias. And it turns out that lots of academic terms in science are actually biased against female names. So basically, if we are discussing Nobel Prizes, scientists, investigators, tenure experts, they're usually more related to male concepts than female concepts. The same thing happened with race. So it's even more biased. So most of the concepts that we analyze that are academic are biased against Black names. That's just not African American names, but Black names in general, include compared to European names. Okay, so I'll stop there. And I think the conclusion of all of this is that, to me, there is a huge opportunity for trying to improve how science is done today with using AI. I show examples in peer review. I show examples in detecting potential problems in images. But I show also that we should be careful about how we use data that has been produced in the past, because it might contain biases. So if we're using recommendations based on text, for example, we should be careful because the text itself contains biases against demographic information. Okay, and with that, I'll finish. And please, if you have any question, unmute yourself and ask away. Thank you. Any question? Okay, I never use, okay, applauses. Thank you so much. So Research Rabbit, let's see. So how many of you use any of these, any like automated method? Like what about connected papers? Nobody? Do you know what connected papers is? I think it's very useful for, okay, question. Oscar.
No question, I just...
Oh, no question, yeah. Yeah, it's a system that allows you to connect papers, and you put a paper as a seed, and then it shows you, you know, how to use it, how the papers are connected.
I also use Research Rabbit and demo it when I'm working with new grad students to kind of show them how to get into the literature and map. It can be a little overwhelming if you're trying to kind of figure out what's been published on your topic already.
Yeah.
I have a question.
Oh, sorry.
Yes, go ahead, please.
Sorry. I just wanted to know, like, how do you think all these research that is done, amazing work by different researchers and you, how these like research can have real world impact from your perspective?
Like in general?
Yes.
Real world. Yeah, that's a really, I mean, that should be the first question that we ask all of us. You know, me personally, I try to think that the things that I'm doing are going to have a very long-term impact in society. So it's very detached really from real world impact. I used to work on things that I thought were more connected to what people do. So I used to work in neuroscience and motor control. So try to tangentially be helping with like Parkinson's disease. So that's very well connected. But science of science, I think, has this very long-term application. Also, one thing that I think is interesting is that when you go, and maybe here our European students can help us, you know, confirm or deny this, but I hear that well, in the world, there is a lot of agencies that are looking up to NIH, for example, NSF, and looking at what they're doing. So sometimes what you do doesn't just affect the US or your particular community, but affects the entire world. And that's just a function of, I mean, NIH is the largest funder in the world. So just a function of how much money they have and how much they move. But it's a really good question. I had students that they're kind of disappointed that science of science doesn't really produce, like, it's hard to even explain to your, you know, friends what you do if you're working on science of science. I don't know if that's kind of what you were looking for.
Yeah, thank you. I appreciate it. I think like just a general opinion, I think science of science is very important, and I think it's very connected to every research domain. And I think like there is a need for like raising awareness in other communities and connecting to different domains of research to make the results that you produce more applicable. I guess so. There are a lot of research areas that do not have any idea that what we do. So I think there is a need for connecting this to other domains. Just a thought.
Yeah, I think that is, and I can cut this. I mean, if this you want to discuss something more, I guess, controversial, but I think there is a huge problem in how students join labs. Like they join and they have we have this idealized view of, okay, I have this amazing idea, I want to work on this. But many times just students join a lab, they have no idea really what things are about. And there is not a lot of thinking about, is this worth doing, right? Is this idea that I'm working on worth, you know, if you're doing a PhD, 5, 6 years of your life, very important chunk of your life working on an idea. I think we should do more of that self-reflection. I don't know what the right answer is, but maybe the science of science can help. I'm excited about, maybe I shouldn't spoil anything, but there are some people working on trying to find perhaps mentors automatically, or at least shortlisting a list of potential mentors. So that's, I think, one way of doing it, but it's just more education from the students as well, and the universities telling you, you know, you can choose whatever you want to do. Don't go to a place because it's famous or because, you know, choose a mentor carefully.
Thank you, and thanks for the great presentation.
Thank you. But that's a problem of the lab, not the student. It's a problem of the lab. Yes.
You have a question if nobody else has raised their hand.
Mm-hmm.
Yeah, it's great that this was NSF funded, and I'm just getting a better awareness of the directorate that funded this program specifically. But what do you see, what does your crystal ball say as far as other funders and their awareness and expectations for, generally speaking, this type of analysis in what they're funding or how they measure research outcomes?
You mean for, let me clarify. So you mean for the specific summer school, or you mean for the research that I presented, or both?
Well, you know, do you see other major funders like, say, NIH, having a better awareness of the tools that are available and how they can improve partnerships and, you know, research outcomes, and actually, for lack of a better phrase, like implementing these methodologies in their evaluation of science outcomes or funding requests? Is that clarified?
Yeah, I don't know how much I should say. I guess now that I have tenure, I can say most things. I think many times they don't want to use this tool because it might expose some holes that they have in their process. I actually went to NSF or NIH, I'll add some uncertainty. And I suggested you use some of these tools. And they were like, yeah, I don't know. We're like, yeah, and I like, go away. And I did the same in the university. I went to Syracuse. Now that I'm leaving, I can say these things. But I talked to I love librarians and everything, but there was like this structure in the library where they were, they have these contracts with these providers as SAC. They would say, I was getting like grant recommendations saying you should apply for cannabis, which is, you know, weed, marijuana research. And I'm like, what is it? What is this recommendation? So that's kind of how this Eileen project started. I think there is a huge resistance to some of these tools, and I wanted to make things open. Like, yeah, there are these things available like Semantic Scholar, and I think Connected Paper is great, but we don't know how they work. Google Scholar is great, but we don't know how it works, how they are ranking things. So I think it will be great if we as scientists kind of take back some of the power that these tools have sometimes, and we can evaluate them and improve them for ourselves. And I hope that funding agencies use them. And but they use some. I mean, they have this. The NIH has a portfolio analysis unit that does a lot of the analysis, and they do great work. But it would be great to. And I'm ignorant, maybe they're using more stuff, but once the one time I suggested, you know, to collaborate, I didn't feel they were like, yes, let's do this, Daniel. And I wasn't asking even for funding. Yeah. Any other question? The other thing that was good, I would say, I don't know if some of you are like developers and developing tools. I think it's very difficult to find funding for developing tools. Like the tools that I develop has been always very difficult to fund. I have to kind of get money from many places to try to fund. So it's very frustrating. I guess it's okay because they want to fund like science, real science, and tool development and softwares. They don't consider real science many times. Okay. And with that, I'll finish my presentation. Thank you so much for listening. Thank you for sticking all the way to the end of the presentations.